All right, so last time we were together, we were talking about tangent and how it relates to sine and cosine and the coordinates in a unit circle. Today we're going to talk about the other trig relationships and reciprocals, different functions that we have that also describe these sorts of coordinates and things. The first thing I want to do is I want to take us through a little bit of a discovery lesson here. So if you remember back in the last session, we talked about how we have the x-coordinate and the y-coordinate of a point on the unit circle. Then we can find tangent by doing the y over the x. Okay, then the tangent, remember, was the slope. So tangent of any angle called theta is going to be equal to the y over the x-coordinate. All right, so now what we need to do is we have to remember that there's actually a relationship already going on here because that triangle is a right triangle. And since that triangle is a right triangle, we can say something about the sides of this triangle that have a relationship. Do you remember what the relationship between the sides of a right triangle is? If you're remembering the Pythagorean theorem, it should be a squared plus b squared equals c squared, where a and b are the legs and then c is the hypotenuse. Well, that's true here too. So we know that x squared then plus y squared should give us 1. All right, so I know I haven't blown your minds at all yet. It's pretty foundational. What we want to do, though, is think of, again, what is our x-coordinate, or how do we find our x-coordinate if all we know is the angle? We find that using cosine. So cosine of our angle squared. Now, when we write cosine of our angle squared, we actually write it like this. So when you see cos squared theta, that means cosine of theta times itself. All right, cosine squared theta. And then y would be sine, and that's squared theta, also equals 1. This is our first trig identity. And I will tell you that this one is muy importante, very important. Okay, so I'm going to just put a nice little red box around that just to highlight how important that particular one is. We use this all the time when we're doing some stuff with trig identities, which we will do in some future examples. So then to carry us forward a little bit further, we have some other functions that I know you've seen before, but maybe you don't remember what we've done with those. So the other functions are secant, cosecant, and cotangent. All right, secant of theta, cosecant of theta, and cotangent of theta. All right, these three are what we would call reciprocal functions. And I didn't spell that very well. Reciprocal. All right, it's spelled up here. reciprocal functions. And they're called that because they are reciprocals of the standard functions cosine, sine, and tangent. So secant is the same thing as saying 1 over cosine of theta. And cosecant, I'm going to run out of room, I didn't do this very well, is going to be 1 over sine of theta. And then cotangent is 1 over tangent of theta. All right, so those are your three reciprocal relationships. Now, cotangent can be a little bit more special because since it's the reciprocal of tangent, and tangent is essentially sine over cosine, then cotangent would be cosine over sine of your angle. So that might come into play as we do some stuff here in a little bit as well. All right, so the first thing we're going to do is we're just going to get an example where we do, for instance, tangent of 5 pi over 3. All right, we'll start with that. All right, well, tangent of 5 pi over 3, if I'm supposed to be finding the exact values, I need to make sure that I'm essentially using that unit circle. And again, tangent of 5 pi over 3 is going to be equal to sine of 5 pi over 3 over cosine of 5 pi over 3. Okay, sine of 5 pi over 3. 5 pi over 3 is this one right here at the 60-degree reference angle. So its coordinates are 1/2 comma radical 3, negative radical 3 over 2. So that means I'm going to have negative radical 3 over 2 over positive 1/2. And then when we break that all down, that's going to end up being negative radical 3 over 1, which is just negative radical 3. Okay, so that's kind of something we already dealt with. But what if I asked for cosecant of 2 pi over 3, for instance? All right, well, that one's a little bit different. That's going to be 1 over sine of 2 pi over 3. Okay, 2 pi over 3 is up here, and its coordinates are negative 1/2 comma radical 3 over 2. And so this is going to be 1 over radical 3 over 2. And remember, 1 over just means that that's a reciprocal. So I'm going to just do the reciprocal of this fraction, and that's going to be 2 over the square root of 3. If you leave it right there, I'll be good with it. But again, if you want to rationalize the denominator and not have a radical in there, then this would be 2 radical 3 over 3 would be kind of the final answer. So either of those two would be just fine with me. All right, so that's kind of your first step into that. Now, the next thing we're going to look at is what if they tell us that we have an angle that's between 0 and we'll just go 0 to pi over 2. Okay, so they're telling us that we have an angle in the first quadrant. And we know that sine of our angle equals, go 2/5. And they want to know what is cotangent of our angle. Okay, well, we're quite a ways away from finding cotangent. If it was cosecant, that'd be a little easier because I'd just have to find the reciprocal of sine. Cotangent's a little bit different beast because cotangent is going to be cosine of theta over sine of theta. Okay, so I'm going to have to find both cosine and sine. I know what sine is. I just have to find cosine. All right, so we know it's an angle in the first quadrant. And so here's what I'm going to do. I'm going to make a little bit of a sketch. All right. What I know for sure is that if I were to make a right triangle in the first quadrant, I know sine, going back to SOHCAHTOA here, SOHCAHTOA. I know sine is my opposite over my hypotenuse. And here's the angle we're talking about. So my opposite side would be 2, and my hypotenuse would be 5. Oh, that makes things really simple. I just have to figure out what this coordinate is right here, and I should be able to figure out cotangent from there. All right, so we're going to do Pythagorean theorem. We're going to do 2 squared plus x squared equals 5 squared. So 4 plus x squared equals 25. X squared equals 21. And that means x is the square root of 21. All right. If x is the square root of 21, that means my cosine value is essentially the square root of 21. And I know my sine value was over 2, so here's square root of 21. So if I want to find cotangent, I'm going to do cosine over sine, which is the same as x over y, which is radical 21 over 2. And that would be an exact answer for that particular situation. So notice that I didn't really use a unit circle here. Instead of making the hypotenuse 1, I made it whatever it said underneath here. We could have done it the other way. I'm going to show you that real quick. And use 2/5 as the sine value and figured out cosine. We would know that, for instance, cosine squared plus sine squared equals 1. And we don't know cosine squared. But we do know that sine was 2/5, so 2/5 squared equals 1. So I'm going to just switch this cosine squared into an x to make it a little bit easier. X squared plus, this would be 4/25 equals 1. Subtract 4/25, we get x squared equals, you'd have to do 25/25 minus 4/25 is 21/25. Then you take the square root of both sides. Okay, it's really not that bad. It's just that it's a different approach, and I know a lot of you would probably struggle doing this way versus writing out a triangle like this. So that's why I chose to do that instead. Now, it's not always going to be in the first quadrant. You know, maybe they tell you that theta is in the second quadrant or the third quadrant. Well, if that happens, then we just have to pay attention. We know that in the third quadrant, this point, okay, it's still a right triangle, but we know that both the x-coordinate and the y-coordinate are negative, and so we just have to make sure that when we are using these numbers, or when we're finally getting, you know, the sine or the cosine or the cotangent value, that we use our negatives appropriately as well. All right, so that's that piece. So then the next thing we're going to do is we're going to learn how to work with our trig identities. Now, I gave you one trig identity. Actually, I've given you like 4 or 5 already. But we're going to have a little cheat sheet here, and I highly recommend you pause the video and you write each one of these down. All right, these are your trig functions, or your trig identities that we're going to use. All right, there's our major one that we talked about. Here are some others that occur on a pretty regular basis. And you can see, again, these 4 and this one we already talked about. These 2 would be new as of right now. And the reason we want to be able to use these is because when you're dealing with math, everything's about efficiency. And if you develop an equation that models something and it has bunch of trig functions in it, like a sine and a cosine and maybe a tangent thrown in there, and you don't have any way of simplifying it, it's going to get really crazy to work with. So if we could actually learn how to simplify things, then it'll make it easier when we go to actually do something with equations. So here's an example. I might have something that says to simplify the expression, and they give me tangent x times cosine of x. All right. Well, typically when they say simplify, they mean you probably want to have just one of your trig functions left if possible. You don't want to have multiples. So we're just going to work through some of our properties to get that to happen. So cosine doesn't really have another property that it goes with. Cosine is cosine. Tangent, however, does have something that it's equivalent to that might help us. So instead of having tangent here, I'm going to rewrite it as sine of x over cosine of x times cosine of x. Okay, so now we might be able to do some simplifying. In fact, if I turn this into a fraction, a lot of you will recognize that since I'm multiplying fractions and I have a cosine on either side, they can get canceled. So then I just have sine of x divided by 1, which hopefully you all know is sine of x. So that is the simplified version of that. Okay, well, what if it got a little bit more complicated than that? Because that was kind of simple. Let's take a look at another one. All right, so let's do, let's simplify 1 minus sine squared t over cosine of t. Okay, this one gets a little bit more interesting. Lots of things we could do here. But one thing I notice here is this says 1 minus sine squared of t. And I don't really have anything here that's equal to sine squared or anything like that. So I'm going to have to go, I'm going to have to try something, right? And the biggest thing about doing these types of problems is trying something that you know is true and working with it and seeing if it gets you somewhere. All right. So I'm actually going to focus on this number 1 right here and the fact that there's a sine squared here. See, I have another identity that has a 1 and a sine squared in it. We're going to use a little bit of substitution here. I can put all of this stuff in for a 1. So that's cosine squared t plus sine squared t minus sine squared t. All right, so I just replaced this stuff right here, replaced that 1. Now this is all going to be over cosine of t. Now you're probably like, listen, Mr. Wilkins, this is not simpler than it was before. And you're right, but I think you could probably tell right now the sine squared t minus sine squared t is going to be 0. So that's going to leave us with just cosine squared t in the top and a cosine of t in the bottom. All right, so 1 starting point, 1 step. This is our second step. And if you remember, cosine squared t just means that I have 2 cosines being multiplied together, which means one of these and one of these can cancel out, and I'm left with just a single cosine t left in the numerator. And now it's simplified. Now I'm going to show you something that's really, really important here that you're going to use in the future, and that is that this property, we call it the Pythagorean identity, that one right there can actually be written 2 other ways. Just solve for either cosine squared or sine squared. So we could also write this as cosine squared t equals 1 minus sine squared t. And you'll see this happen a lot where they give us cosine squared t and we're supposed to substitute 1 minus sine squared in place of it to make it easier on ourselves. Also, sine squared t equals 1 minus cosine squared t. That also happens a lot. In fact, if you take a look at this one right here, 1 minus sine squared t equals cosine squared, that's essentially what we ended up doing. All right, 1 minus sine squared t turned into cosine squared t. So I could have actually done just that if I knew this information before. All right, and that's similar with these other ones. So for instance, tangent squared t equals secant squared t minus 1. And cotangent squared t equals cosecant squared t minus 1, and so on. So we can always manipulate those a little bit. We'll do lots of practice with this in class, so don't get too bogged down in it. That's pretty much it for now. Like I said, we're going to get some good examples in class so you can feel more comfortable with it, but I think that's a good start. Enjoy your day.